thank you for the invitation to speak. So everything I'm going to talk about is joint work with Denis Auroux. And this is somehow a highbrow talk on lowbrow objects, which is usually a bad idea, but I hope it will work out okay. So the setting for the talk is that I have a closed surface genus G bigger than 1, and I ask the question, what is the symmetry group of sigma? Okay, so you could give this many kinds of answer in different contexts, but maybe the most classical answer in a variety of contexts would be to say that this is the mapping class group, so the group of components of the orientation preserving diffeomorphism group of sigma. That's famously also the outer automorphisms of the fundamental group, which is a sort of algebraic characterization of the group, or the fundamental group of the moduli space of curves, which is a sort of natural algebro-geometric incarnation of the group. And Moses' theorem tells us that the inclusion of symplectomorphisms into orientation preserving diffeomorphisms on a surface is a homotopy equivalence. So it also has a sort of symplectic characterization. But this is not the only answer you could reasonably get for the sort of natural symmetry group of a surface. So one example would be that in parts of algebraic topology connected to rational homotopy theory or surgery theory, you would sort of naturally look at the completion of the group ring of the fundamental group, or maybe the Malchev completion of that, the group-like elements in this Hopf algebra, and that has a natural map from the mapping class group to its group of outer automorphisms, and that's not an equivalence. That gives you a sort of strict subgroup. There are interesting automorphisms of this thing associated, say, to immersed curves. And so the question I'd like to ask is sort of what happens in Fleur theory? So just in the symplectic setting, we're used to thinking about, more than just pi naught of simp. So on a symplectic manifold like the surface, in which real H upper 1, non-trivial, we have symplectomorphisms of non-trivial flux. So for each A in H1 of sigma R, I can find a symplectomorphism phi A, well-defined up to Hamiltonian isotopy, which has flux A. So here, if I take a loop gamma on my surface, phi A is isotopic to the identity. If I move gamma through that isotopy, I sweep a little cylinder whose area is given by A on gamma. And simp sigma modulo the Hamiltonian subgroup, so I'll call that G sigma omega, sort of comprises the sort of discrete part, which is the mapping class group, and then also the things that come from symplectomorphisms of non-real flux. So it fits into this sort of natural extension. And this is something we're used to thinking about both in the setting of dynamics and also because of its appearance in Fleur theory. So if we want to ask the question, what's the symmetry group of a surface from the viewpoint of Fleur theory, we should do something to make that question a little bit more formal. There was a sigh of grief and misery, but maybe it wasn't directed at me. So the formalism that we might think about is the formalism of the Fukaya category. So let's suppose that I have a symplectic manifold X omega and I associate to X omega the Fukaya category. So objects are Lagrangians, which it will be important for us are equipped with local systems. In general, you want to look at unobstructed Lagrangians. There'll be more bits of brane data. The morphisms are the Fleur cochain groups. And then there's this kind of mass of higher structure coming from the A infinity structure. And I'll be thinking about the sort of general setting in which one defines this over the sort of universal one variable Novikov field. So sort of C Q to the R. And as we're sort of used to, one typically formally enlarges the Fukaya category in at least a two-step process. So one first forms a category, say, of twisted complexes, so kind of mapping cones and iterated mapping cones. And one then includes idempotent summands to arrive at what's called twist pi of F, or maybe Fx per for perfect modules, sometimes just called the derived Fukaya category of my symplectic manifold. Okay, and we think about these two algebraic enlargement processes somehow as being geometric, you know, at our sort of first naive picture. The passage of taking mapping cones is what we think of as corresponding to Lagrange surgery. So if I have sort of two Lagrangians meeting transversely at a single point, the sort of nicest possible situation, and I think of that point as a morphism from one to the other in the Fukaya category, then the mapping cone is represented by work of Fukaya and co-authors by the Lagrange surgery. And in some nice cases, we can think of taking idempotent summands of some perhaps complicated mapping cone in terms of taking connected components. So a sort of typical example is that you have this pair of curves on the two-dimensional torus which meet at 2 points. You do the Lagrange surgery at the linear combination of both of those points, and up to Hamiltonian isotopy, the resulting Lagrangians disconnected. So including twisted complexes gives you the union of these two curves, but it's reasonable to think you should be allowed just one of them, and that corresponds to taking an idempotent. Okay, but it's definitely not true in general that we can understand all of the objects we get by taking mapping cones or idempotent summands in terms of things that sort of easily fit into this geometric picture. So here are two sort of very standard examples. The first is that in P1 times P1, the quadric surface, we have a Lagrangian antidiagonal two-sphere. Its Fleur cohomology is the same as the quantum cohomology of P1. So that's sort of C of x mod x squared is 1 if we work over the complex numbers. That has non-trivial idempotents, but those idempotents don't live in kind of pure middle degree 2. So it's not obvious how you would go about associating, you know, the homology class of some tentative Lagrangian to them. The idempotents are recording the fact that this Lagrangian bounds holomorphic disks. And a similar flavor example, if you blow up the origin in C2, so you get the total space of the O-1 line bundle over P1. That's a very simple toric surface. It's well known that it has one monotone torus fiber, the one that sort of sits here over the kind of interior kind of vertex, as it would be, of the moment polytope. And that's a non-degenerate critical point of the corresponding LG potential. Its Fleur cohomology is a Clifford algebra. That's just a matrix algebra dimension. So again, that has non-trivial idempotents. And if you take one of those idempotents, the endomorphisms of that object of, you know, that particular perfect module is just rank 1. So that's not something that has Poincare duality. It's not something that could look like the endomorphisms of any closed Lagrangian. So the question that I'm sort of motivated by understanding is, what is the group of autoequivalences of the derived Fukaya category of a surface? So we know that, symplectomorphisms will act on the Fukaya category, and Hamiltonian symplectomorphisms act in a way that, they give autoequivalences that are quasi-isomorphic to the identity. So this group, sort of G of sigma omega, simp mod ham, that I mentioned a slide or two ago, acts on the Fukaya category. And in fact, there's something a bit bigger that acts. Instead of just thinking about symplectomorphisms of non-trivial flux corresponding to H1 with real coefficients, one can also think about tensoring by non-trivial sort of Novikov unitary line bundles. Those give autoequivalences of the Fukaya category, since our objects were Lagrangians with local systems. And so that fits into an action of this sort of semi-direct product, H1 of sigma with coefficients in lambda star, semi-direct product, the mapping class group. And one can ask, is this group that we know quite well that maps to the autoequivalence group, is this somehow intrinsic to the Fukaya category? Does the Fukaya category kind of know the mapping class group, or is it just something that sits there and there's kind of, plenty of other stuff around too? So let me talk briefly through two examples which maybe illustrate kind of what could happen in a nice case versus what could happen in, a different case. So maybe a classical example is the case of a genus 1 surface. So if I think about the torus as just the quotient R2 mod Z2, well then, linear maps that preserve area, SL2Z, just acts on this on the nose by symplectomorphisms. And factoring through sort of simp mod ham, symplectomorphisms act on the derived Fukaya category. And, equivalences of a category will act on the Hochschild cohomology of the category. The Hochschild cohomology of the category just recovers, in this case, by a sort of closed open isomorphism, the cohomology of the torus, with sort of Novikov coefficients. But in fact, in this case, these autoequivalences act in a way that preserves the integral lattice. And so in fact, the sort of obvious homomorphism you had from SL2 to the symplectomorphism group, or maybe to the autoequivalence group, splits. Okay? And in that sense, one might say that, the Fukaya category knew about this SL2Z. Even in this simple case, understanding the full autoequivalence group, which is, somehow built out of this SL2Z and translation and tensoring by line bundles, I think is not so easy to do without appealing to something like mirror symmetry. So here's a non-example of the phenomenon of what you first dream up, sort of, being all there is in the algebra. So this is an old example that I thought about with Mohammed, kind of back in the Cretaceous or something. So we think about this cousin of the A2 Milnor fiber, in which you plumb together a copy of T star Sn with a copy of T star Q, where Q is an integer homology sphere. And well, this has an compactly supported symplectomorphism, which is the Dane twist in the sphere. But to construct the corresponding autoequivalence to the Dane twist, one just really starts from a spherical object in the Fukaya category. So this, exact Lagrangian homology sphere Q gives me a twist functor on the Fukaya category. And if Q is not simply connected, then this autoequivalence is not realized by any compactly supported symplectomorphism.
Ivan, there's a question for you from the audience. Natty, go ahead if you'd like to unmute yourself.
Oh, I'm
I'm not
sorry. I
sure
think that Natty had meant to send that just to me.
Oh, okay. Please, sorry, go ahead.
Yeah, sorry.
I'm not sure if the go-ahead was to a questioner or to me, Shiel.
To you, Ivan, I guess, if there isn't a question.
Okay, fine. So this is a situation in which, you know, the natural map from kind of symplectomorphisms to autoequivalence is not onto. There are autoequivalences that aren't geometric. And, you know, one can wonder what happens in the case of just a two-dimensional surface. Okay, so the theorem that Denis and I prove is that there is a natural surjection from the autoequivalences of the derived Fukaya category of a surface to the mapping class group. And this is deduced from a more technical theorem, which is a kind of geometricity theorem for a certain class of objects in this derived Fukaya category. So, so to state that geometricity theorem, I should just, you know, remind people for a moment that if I give you any kind of DG or A infinity category A, there's a Chern character that goes from the Grothendieck group, that sort of objects mod exact triangles, to Hochschild homology. A more familiar thing would be if I then composed with the open closed map to land in just the homology of my symplectic manifold. And then at least if I started with an object that was a geometric Lagrangian, which was tautologically unobstructed, which bound no disks for some J, then, you know, this composite would just be giving me its fundamental class. So you should think of the Chern character as a substitute for the fundamental class, which makes sense for an object of the derived Fukaya category and not just for a geometric object. And then the geometricity theorem says the following: take X in the derived Fukaya category of the surface, which is spherical, in this sense that, you know, its endomorphisms in the category, so what we think of as its Fleur cohomology, are just the cohomology of the circle. And let's suppose that the Chern character of X is a non-zero primitive class. So this Chern character somehow, at least after composing with the open-closed map, lives in H1 of the surface, at first naturally with lambda coefficients, but it's a lemma that I'm sort of suppressing, that it actually is an integral class. So it makes sense to ask if it's primitive as well as non-zero. So let's suppose we have this, we have a spherical object with non-zero primitive Chern character. And then the conclusion is that this is what you would always want a spherical object to be. It's a rank 1 local system over a simple closed curve. That simple closed curve necessarily then representing a non-trivial homology class. Okay, so let me say a word about how these two results relate sort of one to another.
Ivan, there's a question from Paul. Paul, please go ahead and unmute yourself if you'd like.
Oh, sorry. It's just, is there any example of a spherical object which has a non-primitive Hochschild homology class?
Well, there are, of course, spherical objects that have zero Hochschild homology classes, like a separating curve. So if you mean non-zero and imprimitive, then no, I don't have an example.
Thank you.
Any other questions at the moment?
Sorry, I want to clarify your answer to Paul. So you're saying you don't have an example for why the hypothesis is on the Chern class is necessary?
No, that's not true. I will later show an example of a spherical object whose Chern character is 0, and which is not quasi-isomorphic to any simple closed curve. So some hypothesis is necessary. What I don't have an example of is something whose Chern character is non-zero and imprimitive, but spherical.
Okay.
Probably you could examine our proof and rule this out, but I haven't thought about it. Anything else? Okay. Okay, so the relation between the two results, or the passage from the sort of geometricity theorem to this, you know, detecting the mapping class group, goes via a sort of cousin of the classical complex of curves in two-dimensional topology that was introduced by Schmutz and is sometimes called the Schmutz graph. So this is a graph whose vertices are isotopy classes of non-separating simple closed curves, and where you put an edge between two such curves if and only if they meet with geometric intersection number 1. And what he proved was that the simplicial automorphism group of this graph is the mapping class group if G is at least 3, but this is the extended mapping class group in the sense that it's pi naught of diff. So we're also allowed orientation reversing diffeomorphisms. And it's the quotient of that by the hyperelliptic involution if you're in the special case of genus 2. Okay, so let's think about the following equivalence relation on spherical objects with primitive Chern character. I'll say that x1 is equivalent to x2 if the sets kind of script sx1 and sx2 coincide. S of x is the set of spherical objects with which X has rank 1 Fleur cohomology. So this is sort of rather naturally some kind of, you know, Floer-theoretic attempt to capture the set of edges to which a given vertex in the Schmutz graph is connected, the set of sphericals that you have sort of HF of rank 1. Okay, and what we show, which is not terribly difficult, is that, you know, spherical objects with primitive Chern character up to this equivalence relation are just the same thing as non-separating simple closed curves up to smooth isotopy. Okay? So the kind of isotopy that enters into classical surface topology. On the other hand, the equivalences of the, you know, derived Fukaya category obviously act on spherical objects compatibly with this equivalence relation, which is just in terms of, you know, spherical objects and morphisms in the category. So this defines for you immediately a homomorphism from the autoequivalence group to the simplicial automorphism group, this automorphisms of the Schmutz graph, and hence to the extended mapping class group, more or less. And then a small amount of care dealing with, you know, orientation questions lets you really see that the image of this automorphism sort of is the mapping class group, or lifts when the genus is 2 to the mapping class group. Okay, so why might you care about the main theorem? I mean, opinions will differ. So we include one application in the paper, which I don't want to labor, but let me say just a little bit about it. So this is based on an idea or suggestion made to me a long time ago by Paul, but sort of simplified away from the kind of quite attractive situation he was thinking about to something lower tech. But earlier on, we had this rather simple example of an idempotent inside a Lagrangian torus in the blow up at the origin of C2. So let's just globalize that a little and think about the product of the genus 2 surface and the blow up at a point of the 4 torus, which you should really be thinking of as sort of the blow up at a copy of the genus 2 surface of sigma times T4. And we'll think about symplectic forms on this that look like a kind of standard symplectic form on a blow-up, a product symplectic form plus a little bit of exceptional divisor, but perturbed by some sort of irrational form, which has sort of generic coefficients in H2. And from the fact that H1 generates the cohomology of both the surface and the 4 torus, if I take kind of suitable rationally independent combinations of wedge products of one-dimensional cohomology classes, then when this irrational part is indeed generic, then any symplectomorphism of X which preserves this modified symplectic form will have to act trivially on the cohomology. On the other hand, by using this idempotent of this Lagrangian torus that I had before, I can build a functor from the Fukaya category of the surface to the Fukaya category or the derived Fukaya category of this product X, which just multiplies a simple closed curve by this torus and then takes the obvious kind of idempotent in the Knuth decomposition. And, you know, what this functor really does is it identifies a summand of the Fukaya category of X corresponding to a particular C1 eigenvalue with the derived Fukaya category of the surface. And using this, one sees that, you know, autoequivalences of the Fukaya category of this blow-up map to autoequivalences of the Fukaya category of the surface and hence to the mapping class group. But because we know all symplectomorphisms are acting on cohomology trivially, the parts of autoequivalences that actually come from symplectomorphisms of X with respect to this sort of perturbed symplectic form must be mapping to the Torelli group. And the Torelli group is an infinite rank free group in genus 2, and one doesn't, you know, quite get a clean statement of a symplectic manifold with infinitely generated mapping class group, but one finds on this example a sort of sequence of symplectic forms for which the rank of the symplectic mapping class group is unbounded. And this is, you know, I mean, if you think about high-dimensional symplectic mapping class groups, this might appeal. If not, it's a sort of, you know, rather technical result. I don't want to kind of, it's not the be-all and end-all of the theorem, but it is a situation in which it was natural from the setup to be thinking about the derived Fukaya category rather than just something sort of more naively geometric. But, you know, we also know in the setting, for instance, of mirror symmetry that it is this kind of category of perfect modules that typically shows up. So it seems to me like a reasonably natural question to try and understand the Fukaya category of something as simple as a surface, in particular as part of understanding it and the derived category to understand the autoequivalence group. So the other thing I think is, you know, that's potentially appealing about this result is not the result itself, but the proof, which is kind of a nice amble through all sorts of bits of, you know, contemporary Fleur theory, but applied in a rather concrete case. So what I'd like to spend the second half of the talk doing is just, you know, walking through the steps of the argument. And I won't be able to say very much about any given one because we use a lot of, you know, beautiful machinery developed by other people, but I hope I'll give some sense of the kinds of ingredients that get employed, and maybe, you know, if you've seen those ingredients in an abstract setting, the idea that it can be used to think about curves on surfaces and their derived analogues might seem like a reasonable sort of motivation. And things really start in some sense with some beautiful work from now a few years ago by Haydn, Katsakov, and Kontsevich, who studied Fukaya categories of non-closed surfaces, and they proved a kind of remarkable geometricity theorem for the objects of such categories. So their setting was that they had a surface with sort of boundary and punctures, and typically with some sort of stops, so some marked points on the boundary, and they also worked in a graded situation, so their surfaces came equipped with line fields. And they showed that if you studied the category of twisted complexes over the Fukaya category of such a surface, either the compact or partially wrapped Fukaya category relative to these stops, and you took any object in twisted complexes, then it was geometric in the sense that it's quasi-isomorphic to some union of immersed curves with local systems. And really, now I mean a union, so something that sort of lives in what you think of as the additive enlargement of the Fukaya category, just a bunch of objects sitting there and not interacting via the data of a mapping cone. So the sort of, their story is very beautiful, but the key ingredient is that partially wrapped Fukaya categories of surfaces with boundary admit kind of quiver algebra models. They're described by quivers with relations. And this comes by choosing very special sets of generators for these categories, which they call full formal arc systems. So these are collections of pairwise disjoint arcs, which cut your surface into a bunch of disks. So I've drawn unwrapped in the case of a torus with two boundary components, one possible example of such a full formal arc system. And then you write down a quiver whose vertices are these arcs, and the morphisms come from the Fleur complexes between these arcs, which are generated by the allowed segments of Rabe chords at the boundary components of the surface. But there aren't too many morphisms because the presence of these stops prevents you from rotating around too far on the boundaries. And then there's a product amongst these generators. So there's a non-trivial mu2 in this category, which tells you how to concatenate arcs in this quiver, and some products are zero, and that gives you relations in this quiver. And by a kind of generation statement, the partially wrapped category is completely encoded in this kind of quiver with relations. And so then any twisted complex gives you a module over this quiver, and they classify modules of certain particular kinds via some sort of linear algebra problem that comes from beautiful work of Nazarova and Reuter from quite long ago in sort of related problems. It also showed up in classifying objects in derived categories of elliptic curves separately in work of Bourbon and Drost. But somehow from the outset, this is not something that we can hope to directly imitate if we're starting with a closed surface, because, you know, we don't have arcs, and moreover, we know from beautiful work of Paul back when he wrote his book that these categories are not formal, and we don't expect to write down some collection of generators for the Fukaya category of a closed surface in which there's only mu2. And that's somehow, you know, at the heart of what enables them to make these linear algebra problems completely tractable. But nonetheless, we will lean on their work very heavily. Okay, so let me come back to a cautionary example, which I mentioned when Paul and Mohammed were asking questions earlier. So if I take a separating closed curve on my genus 2 surface, and I start to bend it around, as in this middle picture, I just bent that so that you could see that I could push the curve through itself, as in the right-hand picture. And now I have an immersed curve, and it has these two self-intersection points, but they bound exactly one, you know, holomorphic strip. So from the point of view of Fleur theory, the new generators in the Fleur complex I added get cancelled by this unique strip. And this is still a spherical object to this immersed curve. It doesn't bound any teardrops, so it's a perfectly happy, unobstructed object of the Fukaya category. On the other hand, if somehow the area of this lobe that I push through is larger than the area of this kind of region that I used to bound sort of over here, well, then there's no room to undo this push by moving X by zero flux. In other words, by something that could be a Hamiltonian isotopy. And starting from there, you see that this is a spherical object, which is not actually quasi-isomorphic in the category to a simple closed curve. Of course, this is an example in which the Chern character of the object, which I told you was some sort of corrected version of the fundamental homology class, is zero. So the first thing that we have to address is that the output of Haydn, Katsakov, and Zavich's work will be a geometricity theorem that tells us everything looks like a union of immersed curves with local systems. But in order to connect to things like the Schmutz graph, we're going to want to get down to embedded curves. And the heart of being able to do that is somehow the following cartoon. So suppose I have a geometric object, it is an immersed curve, which I know is spherical and whose Chern character I'm told is primitive. And I'm on a surface which is not compact. So I have some boundary or punctures. And then the claim is that X is quasi-isomorphic to what we want, a rank 1 local system on a simple embedded curve. Okay, and how will we do this? Well, X is immersed. So if it's spherical, then first one shows that it must bound some bigons. So somewhere there's a bigon like this. Actually, there's not really a bigon like this because X itself could run through all the bigons, but this is an iterative process. But suppose we have a simple bigon like this, which from the point of view of X looks kind of empty. It doesn't contain any more of X. And we would like to deform X to cancel this away and simplify the total number of self-intersections. And this primitivity hypothesis on the Chern character means that we can find an arc that goes from a point P inside this bigon out to infinity, but which has total algebraic intersection number 0 with X. Okay. And once you have that, what you can do is start pushing X along this green arc gamma. So each time you see X meeting gamma, just deform it locally by pushing it along gamma a little bit, as in this orange curve on the right. And we do this by a sort of uniform local model at these intersections. So the fact that this algebraic intersection number was 0 means that altogether I'm sweeping 0 area. And so this is locally a Hamiltonian isotopy. But this has the function of pushing kind of one side of X towards the other side as regards this bigon. So I sort of shrink the area of this bigon. And eventually I shrink it to be kind of smaller than everything else around. And then I can do some kind of local cancellation, sort of inverse to just introducing a silly pair of cancelling intersection points by pushing a curve through itself. Okay, so this is the origin of this hypothesis on the Chern character. It's what lets us pass from geometric objects, sort of immersed curves with local systems, to, in the spherical case, things that are actually embedded curves and hence to connect to this Schmutz graph. Okay, so the one-line description of the strategy then is that we want to reduce from studying things on a closed surface to studying things on a surface with boundary. So we can use this HKK geometricity theorem and this kind of classical topology as just described. So if you believe the output of the theorem that Denis and I prove, and you take one of these spherical objects, secretly it's represented by some simple closed curve. So if you pick a point far away on your surface sigma, it doesn't feel like your object should talk to that point at all. it kind of, why don't you just put in a little boundary component there? The trouble is that, a priori, all we have is, some idempotent pi written in a twisted complex on some set of split generators for our category, for instance, a standard A to G chain. And the idempotent that enters into this twisted complex is built out of holomorphic polygons, and some of those holomorphic polygons could perfectly well run over this point, wherever I put the point. So we didn't find at least any reasonable way of saying one could just puncture the surface and preserve the property that this idempotent existed, that the corresponding Fleur cochain was still a cocycle and still satisfied the idempotent property. So we're going to do something different. There's a separate point to note, which is that HKK studied twisted complexes on the Fukaya category of a surface with non-empty boundary. And we're trying to study the full derived category, so split closed twisted complexes. And they also studied things in a graded setting, and the Fukaya category of a surface is only Z mod 2 graded, and it has simple closed curves that don't admit a grading structure for any choice of grading on a subsurface. So, so there are sort of some updates to HKK that need to get made along the route. So maybe the heart of what makes things work is work of Heather Lee, inspired by a sort of, again, now almost historical in the wake of all the subsequent work of Ganatra, Pardon-Chende and others, but in an early picture of the idea of sheathifying the Fukaya category, Paul wrote a short paper on covering things by pairs of pence and trying to build the Fukaya category by sort of from Fukaya categories of local pieces. And this idea was implemented very beautifully for the case of, in fact, very affine Riemann surfaces by Heather Lee, but her technology adapts to give a description for Fukaya categories of closed surfaces. So I have a closed surface sigma, and I fix some annulus A, neighborhood of my favorite simple closed curve, and I actually fix an annulus A with kind of, sort of extra little side annuli at the ends. And then I'll introduce a surface with boundary S, which is not quite a subsurface of sigma. It will be sort of something that maps to sigma, but covers this sort of inner annulus A twice. That gets kind of included at both ends. And then I have just separately, lonely on its own, the annulus A itself. And Heather Lee constructs sort of restriction functors. They're constructed by picking a particular set of split generators for the category. So you have to pick objects that lie kind of well with respect to this annulus A. You don't want things that, for instance, backtrack in A, but you choose some set of split generators that move nicely through A. And she constructs restriction functors from the Fukaya category of sigma to the wrapped category of S, and a pair of restriction functors from the wrapped category of S to the wrapped category of A. And that exhibits the Fukaya category of sigma, or its derived category, as a kind of pullback. So Fleur complexes in sigma become identified with the kind of subcomplexes of the wrapped categories of objects of S, which have the same restriction under these two functors to the wrapped category of A. And the geometric heart of Heather's procedure is this sort of beautiful implementation of a kind of telescope type model for the Fukaya category of sigma. So you take a curve that runs through this annulus, and you twist it a lot in the annulus, but somehow altogether no times. So you twist it, say, 2n times in this middle annulus, and minus n times in each of the outer annuli. So if you just looked inside the middle region, you would see what looks like the appropriate wrapping for the wrapped category of A. And if, on the other hand, you somehow stood inside the main body of sigma and looked at one of the ends, you would see what looked like the appropriate wrapping for a wrapped category at that end of the subsurface. And Heather proves a kind of non-crossing theorem for holomorphic disks that says that if you have a holomorphic polygon which is not completely contained in this middle region, then its output lies in the middle region, at least once you've twisted enough relative to a fixed set of endpoints. So she sort of exhibits things that happen in this middle part as some kind of A infinity ideal. That's where that, together with things just coming from inclusion of subsurfaces, is where these functors come from. Okay, so we get the following proposition. Suppose I take a twisted complex on the Fukaya category of a closed surface, and suppose I know that it has trivial Fleur cohomology with some simple closed curve gamma. Then, in fact, X is geometric. In other words, X is quasi-isomorphic to some sum of immersed curves with local systems. And where does this come from? Well, we look at this restriction functor to the surface S as drawn a moment ago. The image of X under that restriction functor has some HKK replacement. In general, that HKK replacement could contain sort of boundary parallel curves, things that live in this annulus A that was sort of included twice in S hat. So you need to do some correction there because, you know, those come up in pairs which restrict to the sort of corresponding same annulus in the middle region. So that's part of this pullback data. But up to some delicacy with boundary parallel summands, what you show is that this sum of immersed curves with local systems can really be pulled back into sigma minus A. So it lives inside, in particular, your original surface sigma. So this is at the level of twisted complexes. We want a version that also lets you take an idempotent summand of a twisted complex. And here we do something kind of, you know, there's a roundabout detour into significant technology because, you know, just as the HKK strategy doesn't immediately adapt in any obvious way to a closed surface, it also doesn't immediately adapt in any obvious way to an idempotent. But Lee proved this sort of sheafification of the Fukaya category in this case in order to prove a mirror symmetry statement. She proved that the derived Fukaya category of a surface with punctures is the split-closed category of singularities or matrix factorizations on some mirror Landau-Ginzburg model. And in earlier work, Abouzaid, Auroux, Efimov, Kadzakov, and Orlov, building on kind of classical work in algebraic surface theory, had given a sufficient criterion for the derived category of singularities to be split closed. And this turns out to be true if and only if the first negative K-theory of the category of perfect complexes on your singular algebraic variety Z vanishes. And K-1 is something that one can actually compute for unions of toric surfaces because it has kind of reasonable Meyerbeer-Torus type sequences. So there's an interesting point here, which I don't want to labor, which is that, you know, there are different mirrors that have naturally shown up in the literature to the wrapped Fukaya category of a surface with punctures. For instance, there are other mirrors to Heather Lee's that come up in work of Catherine Canizzo. And it's not true that this condition holds for all of them. But, you know, there is a mirror in which one can show that the derived category of singularities is split closed. And actually our argument for that relies on the surface having enough punctures because it relies on being able to appeal to certain kind of toric pictures of a surface with punctures. So we end up with the following proposition. If S has at least 3 punctures, twisted complexes on the wrapped category of S is already split closed. And this actually works even in the Z mod 2 graded case. And in particular, if you take any object X in the split closed derived category of a surface, now a closed surface sigma, okay, so this is the kind of thing we want to study. And if you can find two different simple closed curves, gamma 1 and gamma 2, which are linearly independent in H1, which X is orthogonal to, then by restricting to some S, which is the complement of two different annuli, you can show such an X is geometric. Okay, so we don't have a geometricity statement for the whole of the derived Fukaya category of a surface, but we do have something for objects that are disjoint Floer-theoretically from a couple of simple closed curves. Okay. So what we still have to do is find these simple closed curves. Where are these gamma I going to come from? And we only want to find in the case where X is a spherical object with primitive Chern character. At least that's all we need for our application. Okay, and this comes from machinery in equivariant Fleur theory. So there's a kind of digression on various beautiful ideas introduced over the years by Paul and others. So if I take an integral cohomology class on a surface, I think about a prime P, I have a Z mod P action on the Fukaya category coming by tensoring by flat unitary line bundles. And my class A also defines a homomorphism from the fundamental group of the surface to Z mod P, just given by the obvious homomorphism to Z and then reduction of coefficients. So that gives me a p-fold cover sigma Twiddles of my surface, and that has a group of deck transformations. And if one pays attention to, which is not the kind of thing I can possibly do in real time on a screen, then if this was the group G, then the deck group is naturally the kind of Pontryagin dual group, sort of HOMS from G to C star. And there's a sort of well-known relation between Fleur cohomology sort of downstairs and upstairs in covers because holomorphic disks lift uniquely to covering spaces given a lift of part of the boundary conditions. So if I take some collection of split generators for the Fukaya category of sigma, and I could choose those all to lie in the kernel of this sort of homomorphism associated to A, then, well, so those are curves, say simple closed curves on which A evaluates trivially. That's saying that they admit equivariant structures for this G action. Choosing such an equivariant structure is like choosing a lift of the curve to the cover. And indeed, I can somehow understand the kind of Fukaya category of all the possible lifts upstairs. So the direct sum of the Fleur complexes of not just our chosen lifts, gamma I Twiddles and gamma J Twiddles, but those kind of twisted by characters, which in terms of this deck group action means moved around by the deck group. This whole algebra gets identified with a kind of semi-direct product algebra of my finite group and my original Fukaya category downstairs. Okay, so if I have a rank 1 system on a simple closed curve gamma, so if A evaluates on the homology class of gamma to 0, that's saying that gamma admits an equivariant structure. So in fact, it admits P different such, differing by characters of the group, and correspondingly gamma admits a lift to this cover, and of course it then admits P difference such. And if I now pick another sort of unrelated closed curve delta on which A also vanishes, so delta also lifts as a closed curve, indeed has many lifts to this covering surface sigma Twiddles, then the Fleur cohomology of gamma and delta downstairs gets written as the sum of the Fleur cohomology of my preferred lift corresponding to my equivariant structure on gamma with all the possible lifts of delta. And the point is just that this is now a direct sum indexed by P things, the size of my group. So if P is big, some of these objects on the right must be 0. I mean, some of these summands. Because the left-hand side is some fixed rank thing and the right-hand side is indexed by P things. So if I gave you a spherical object with non-trivial primitive Chern character, the sort of thing I care about, if I could make it Z mod P equivariant for sufficiently large P, then in some cover, the fact that it's equivariant would mean that it lifts to an object upstairs. That's what we described on the previous slide. And then this identity would say that upstairs, this lift X Twiddles would indeed be Floer-theoretically orthogonal to a bunch of disjoint closed curves, as many as I wanted, for P large. Then our previous restriction arguments would let us conclude that this thing upstairs was geometric. Then we could push that geometric thing back down to sigma, and then we could go back to the topology of immersed curves on surfaces and try and argue that X was just a simple closed curve. So what we would like is some reason for an abstract X about which we only have these kind of categorical bits of information to be Z mod P equivariant. And in this setting of finite group actions and equivariance, we don't know how to proceed. But thankfully, Paul also developed a beautiful story about equivariance with respect to continuous group actions. So our class A in H1 of the surface actually defines a rational action of the multiplicative group on the Fukaya category of the surface. Sorry, that X should be a sigma. So this is given, you know, the multiplicative group is R times the unitary Novikov group. I can push Lagrangians around by symplectomorphisms of flux S times A, and I can tensor objects by unitary line bundles with sort of holonomy given by the value lambda in the unitary Novikov group. And one can make these actions strictly commute, so one can really build a strict action of the multiplicative group. And if I choose A such that this cohomological condition holds, that's somehow exactly what's required to say that my object X is infinitesimally equivariant for this action, in the sense that a natural kind of deformation class, which measures kind of infinitesimal differentiation of the object in the action, vanishes. But in characteristic 0, there's a machinery that Paul developed for upgrading infinitesimally equivariant objects to weakly equivariant ones. That's to say, things that behave as if they're equivariant from the point of view of the cohomological category. But if you're weakly equivariant for the full multiplicative group, you're a fortiori weakly equivariant for a finite subgroup of the multiplicative group. But again, there's a technology for finite groups to upgrade weakly equivariant modules to actually equivariant modules by kind of obstruction theory arguments that come down to the fact that group cohomology for a finite group with coefficients in a module in, say, characteristic 0 vanishes. And that's where the vanishing of these obstructions comes from. Okay, so at the end of the day, we take our abstract spherical object, we make it GM equivariant, hence finite group equivariant. Given an equivariant structure, we get an object in a covering surface. We use the restriction technology of Heather-Lee to get an object in the derived Fukaya category of some non-compact surface. Mirror symmetry tells us that was actually a twisted complex up to quasi-isomorphism. HKK give us that that was a union of immersed curves, and then some classical surface topology gets us all the way back to a simple curve. So it's a surprisingly involved story for loops on surfaces. I'm sorry I've overrun, but that's it.
Okay, well, let's thank Ivan for his talk. Questions for Ivan? There's a question from Egor. Egor, go ahead.
I was just wondering, so how far one can go using just, say, fixed point Fleur homology towards this higher dimensional MCG application that you have presented?
Yeah, I don't know. I haven't thought about that. That seems like, I mean, I would expect there to be other ways that you could build examples of this phenomenon. What I originally wanted to do was build something whose symplectic mapping class group would be the Torelli group, so an infinite rank free group, and I didn't, we didn't manage to do that. So this was an example that came up in the context of trying to realize a particular thing. Yeah, that seems like a good question, but I haven't thought about it.
Thank you.
I had a question, Ivan, which maybe I'll ask right now while there are other questions yet. Just a question about your use of the Viterbo restrictions that Lee developed. So typically, I think of these Viterbo restriction functors as being associated to like exact embeddings of Liouville subdomains, but of course, we're not in that situation here. Am I supposed to think that the reason it works is because, well, the complements of these Liouville subdomains don't bound disks, and so somehow all the technology just goes through, or is it, can you comment on that?
Yes. I mean, so we need to exclude, as I said, curves that somehow backtrack and would give you obvious holomorphic disks that would misbehave. And the actual restriction functors involve kind of, as a technical point, action rescalings, because you're already working with Fleur complexes that are defined over the Novikov field. But somehow anything that you thought might look like, more a Cartan element in symplectic cohomology or something isn't there. So if you tried to apply Heather's technology to cut out a disk from a surface by picking a null homotopic embedded simple closed curve, you would definitely hit issues, but we don't do that.
That makes sense, thanks. There's a question from Mohammed. Mohammed, go ahead.
I just wanted to, so it seemed to be much harder to improve the statement from like the triangulated closure of Lagrangians to the idempotent closure. Is there, I mean, of course, I assume this application requires it because there is this summand that lives in the
right. I mean, somehow, yeah. I mean, the equivalences of this blow up are acting on this summand of its Fukaya category, but if you want to identify that with something that comes from sigma, what you're going to learn is that a set of split generators for it, as you feed into something like Scheele or your criterion, come from the surface. And I think there are other situations in which, it's more natural to have the split closure. I mean, it's also true that the split closure is what usually comes up when you prove mirror symmetry. But yes, I mean, it's true that it involves definitely some additional amount of work to get the idempotent.
Okay, thanks.
That's it, kids. You can go.
Okay, well, if there are no other questions, let's thank Ivan again, and we'll transition after this to the discussion session. Thanks again, Ivan.